Hello students, welcome to this channel. In this video, we're going to talk about the most important questions from the chapter Chemical Bonding for Mains 21. So chemical bonding basically is a very important chapter in mains point of view. Every year you get to see 1 to 2 questions coming from this chapter. So it's important we master chemical bonding, and we also need to learn how to solve the questions of chemical bonding in less time so that we can save up time in this chapter and invest it in solving organic chemistry questions in the exam hall. Anyway, in this video, we're going to work on a few previous year questions, especially from 2019 and 18 question papers of mains, and we'll also understand a few shortcuts wherever necessary. So let's get started with question number 1. The ion that has sp3d2 hybridization for the central atom is. There are 4 options over here, and you need to look at the central atom in each of these options, and you have to identify the hybridization of the central atom in each of these options. And identify the one which has got sp3 hybridization, sp3d2 hybridization among these 4. This question is being taken from JEE Main 2019 8th April Shift 2 question paper. This is pretty recent one then, and look how easy the question is. In order to find the hybridization, you just need to use a simple formula, and the formula looks like this. The number of hybrid orbitals H is equal to half into the total number of valence electrons present in the central atom plus the total number of monovalent atoms present around the central atom minus the total cationic charge present on the molecule plus the total anionic charge present on the molecule. Through this formula, you are calculating the total number of hybrid orbitals. If the total number of hybrid orbitals is equal to 2, then hybridization is sp. If it is equal to 3, then hybridization is sp2. If it is equal to 4, hybridization is sp3. If it is equal to 5, then hybridization is sp3d. If it is equal to 6, then the hybridization is sp3d2. If it is equal to 7, then hybridization is sp3d3. So by observing the number of hybrid orbitals, you have to find the hybridization. Let us apply this formula for all the 4 options that we have. Option 1 is ICl2. The halogens like fluorine, bromine and iodine, because they belong to group 17 of periodic table, they contain totally 7 valence electrons in the outermost shell. And over here, since I'm talking about iodine, even for iodine, the number of valence electrons V is equal to 7. Followed by around iodine, I see 2 chlorines. Chlorine is monovalent. So 2 chlorines is 2 monovalent atoms, and M value is equal to 2. And then on the overall molecule, I see -1 charge. So over here, the total anionic charge A is equal to -1, and there's no cationic charge. So C is equal to 0. When we substitute the values and simplify this formula, H turns out to be 5. And when H value is equal to 5, hybridization is sp3d. And similarly, when you solve it for BrF2 minus, ICl4 minus, IH6 minus, the number of hybrid orbitals come out to be 5, 6 and 7 respectively, and thereby you can figure out what hybridization is. But in the question, they asked us to find out the molecule with sp3d2 hybridization, and according to what we have calculated, the molecule ICl4 minus has got this hybridization, so the right answer is option C. I hope you understood how to deal with this question. Please make sure you learn this formula to calculate hybridization. This is very important. Now moving on to the next question, and this question is being picked up from the paper of Mains 2019 8th April Shift 2, and the question is talking about identifying the molecule which is diamagnetic and has got the shortest bond length from the given 4 units over here. So in the question, we have 4 molecules given, and the first one is C2-2 followed by N2-2, O2-2 and O2. Out of these 4 molecules, you need to identify the one which is diamagnetic and has got the shortest bond length. This is one of the most important patterns from chemical bonding. From all the topics of chemical bonding, molecular orbital theory and the questions related to it are very prominent. You get to see the question from MOT definitely every year. Let it be related to magnetic behavior or bond length or bond order or bond strength or maybe the number of unpaired electrons or whatever. About MOT, you have a question every year. So make sure you learn and practice MOT properly. And how do we deal with this question? Over here, you got to identify two things. The first one is magnetic property. You need to identify which molecule is diamagnetic by nature, and the molecules which contain zero unpaired electrons are called as diamagnetic molecules. So out of the four anions, you need to identify the anion which has got the diamagnetic nature by observing if it is having zero unpaired electrons or not. And the second thing that you need to observe is the shortest bond length. The bond length and bond order are inversely proportional to each other. So from the molecules that you see, from the species that you see here, if you can calculate bond order, because bond order is inversely proportional to bond length, you'll be able to compare bond length. So these are the two things that we have to be doing. Let's get started with step 1. Let's identify the number of unpaired electrons in each case and figure out which molecule is diamagnetic. Then let's talk about bond length and bond order. Over here is the solution already written. Observe the solution. In the molecule C2 minus 2, since you are talking about C2, it's 2 carbons. Technically, you should have 6 plus 6, which is 12 electrons. But because you are having a minus 2 charge, to this 12 electrons, you must have added 2 electrons more, which is 14 electrons in total. And according to molecular orbital theory, how do you fill up the electrons? You fill it up from 1s, then 2s, and then comes 2p, isn't it? And in 1s, when you apply the linear combination of atomic orbitals, then what happens? You'll be having 1s of first carbon and 1s of second carbon molecularizing, leading to formation of sigma 1s and sigma star 1s, isn't it? Similarly, you will have over here in the second level sigma 2s and sigma star 2s, right? So how many electrons can you fill up over here? In sigma 1s, you can fill 2 electrons. In sigma star 1s, you can fill 2 electrons. Similarly, in sigma 2s, you can fill 2 electrons. And sigma star 2s, you can fill 2 electrons. So out of the 14 electrons that you have over here in C2 minus 2, 8 electrons are filled in sigma 1s, sigma star 1s, sigma 2s and sigma star 2s, right? So from here you can understand that out of the first 8 electrons in these molecules, the 4 electrons are bonding electrons and the remaining 4 electrons are anti-bonding electrons, correct? So thereby we don't need to worry about the first 8 electrons in any of these molecules. So out of 14, 8 electrons is sorted. Now I just need to worry about remaining 6 electrons. And when I look at electronic configuration, the remaining 6 electrons in C2 minus 2, which has got 14 electrons, are arranged as 2p x2, 2p y2, 2p z2. Out of these 2p x, y, z, the first two are pi and the second one is the sigma bond. But anyway, at the end, all of them are bonding, isn't it? So ignoring this 8 electrons, because they are common in all the molecules, isn't it? These 8 electrons in 1s and 2s are common in all the 4 sets, so I'm ignoring them. But technically, you can take them also into consideration when you calculate bond order, when you check magnetic behavior. But all of them are 2 since they are paired, and all of them are common amongst the 4 molecules that you have. So I'm ignoring the first 8 electrons and I'm going ahead with the remaining. So out of the remaining 6 electrons in C2 minus 2, all the 6 electrons are bonding electrons. So when I have to calculate bond order, which is nothing but the total number of bonding electrons minus the total number of anti-bonding electrons divided by 2. When I use this formula, it has to be 6 minus 0 by 2 because 6 bonding electrons, 0 anti-bonding electrons. I will be having what? I will be having the bond order achieved to be 3. But then the point is not about calculating bond order. In the first place, we should see the magnetic behavior. We should see if the molecule has got any unpaired electrons so that we can decide it to be para or dia. Diamagnetic species have 0 unpaired electrons. Paramagnetic species have at least 1 unpaired electron. And when I look at the electronic configurations over here, it is 2px2, electrons are paired. 2py2, electrons are paired. 2pz2, electrons are paired. And hence, the molecule C2 minus 2 has got 0 unpaired electrons and hence it is diamagnetic. Similarly, when we apply the same set of logics for O2, which has got 16 electrons, and ignore the first 8 electrons because they are anyways present in sigma 1s, sigma star 1s, sigma 2s and sigma star 2s, you have to observe the remaining 8 electrons. And the remaining 8 electrons are present in this manner. And how do we get to know in which manner are they present? For this, you need to draw the molecular orbital diagram. And by drawing molecular orbital diagram, we will be able to understand how many electrons are present in which subshell. And according to this particular electronic configuration, you're having 6 bonding electrons and 2 anti-bonding electrons. See, here is one anti-bonding, here is one anti-bonding. And rest everything is bonding electron, right? So it is 6 minus 2 divided by 2 according to the formula of bond order, which is bonding electrons minus anti-bonding electrons divided by 2. And when I calculate bond order, it's equal to 2. And when I look at the configuration, I have 2 single electrons or 2 unpaired electrons. So this molecule is paramagnetic. And using the same set of logics, the third molecule has got 0 unpaired electrons, diamagnetic, and its bond order is equal to 1. And the fourth molecule has bond order 2 and it is also paramagnetic. So according to the question, we need to figure out the molecule which is diamagnetic. So how many diamagnetic molecules you have over here? We are having diamagnetic molecules 2, the first one and the third one. But we need to observe the diamagnetic molecules which contain the shorter bond length, isn't it? With shortest bond length. Bond length and bond order are inversely proportional to each other. We are observing the bond order of those 2 diamagnetic molecules. The first one has got bond order 3 and the second one has got bond order 1. So if the first one has got highest bond order, its bond length must be lower. And if the second one has got low bond order, its bond length might be higher, right? So the shortest bond length and diamagnetic molecule is what is given in option A. To brief whatever we have discussed over here, we are talking about a question which is asking us to identify the molecule which is diamagnetic with shortest bond length among the 4 molecules given, among the 4 options given. So diamagnetic molecule is the one which has got 0 unpaired electrons. So we need to look at the molecular orbital diagram or electronic configuration, figure out if you have any unpaired electrons over here. And from this we understood that out of the given 4 options, option 1 and option C has got diamagnetic behavior. And then we started observing the molecules which have got the shorter bond length. And the relation between the bond length and bond order is inverse. By observing the bond order and by inversing the relation, we can compare the bond lengths as well. So according to the question that's been asked to us, option A is the correct answer. I hope you could understand this, but in case of any doubts, please let me know what your doubts are in the chat box below, in the comment section below. So moving on to the next question for now. Among the following, the molecule which is expected to be stabilized by anion formation is. There are a few molecules C2, O2, NO and F2. You need to identify the molecule which can be stabilized by formation of the anion. As in, if I take C2, if I convert this into anion C2 minus, will this get stabilized? Will C2 minus be more stable than C2? Similarly, if I take O2 and turn it into its anion, will O2 minus be more stable than O2? And if the same is done with NO, will NO minus be more stable than NO? And if the same is done with F2, if F2 minus be more stable than F2? So this is what is the question talking about. And this question is picked up from Mains 2019 April Shift 1 question paper. Let us see how to solve this question. There are multiple ways of solving this. In fact, you can observe the stability by observing the electronic configurations also, but that might be a little lengthy process. So let us compare stability on the basis of bond order. So bond order and stability are directly proportional to each other. If the bond order of a molecule is higher, that molecule also will be more stable. So if bond order increases, stability increases. If bond order decreases, stability decreases. So in all these 4 conversions, conversion 1, conversion 2, conversion 3, conversion 4. In all these 4 conversions, we need to see where exactly the bond order is increasing. Okay. And how do we calculate that bond order? First of all, we can do it with the help of so-called taking bonding electrons, anti-bonding electrons and all of that, but that's gonna take a little longer time. So here is a shortcut to be able to calculate the bond order. With the help of the shortcut formula, you can calculate it. So shortcut number 1, if the total number of electrons that you are having the molecule is either 1 or maybe 2. If the total number of electrons in the molecules is equal to 1 or 2, use the formula n by 2, where n is equal to the total number of electrons. Alright. And if the total electrons is between 3 to 6, then use the formula 4 minus n by 2. Similarly, if the total number of electrons is between 7 to 14, use the formula 8 minus n by 2. And if the total number of electrons is between 15 to 20, use the formula 20 minus n by 2. By using this formula, you can readily calculate bond order. I'll give you examples to get this better. In case of C2, I have 12 electrons totally. One carbon has 6 electrons. C2 is 6 plus 6, 12 electrons, right? Because it has got 12 electrons, I should be using the third formula. 7 to 14 is the range of electrons here, right? So 12 electrons fall between 7 and 14. So I can calculate the bond order of C2 using this 8 minus n by 2 formula, which is 8 minus total electrons 12 divided by 2. Which is equal to how much? Which is 4 by 2, which is equal to 2. You don't need to bother the sign. It's okay if it is plus or minus. The bond order of carbon over here is 2. On the other hand, when you look at C2 minus, because one electron increase, there are 13 electrons totally, and 13 electrons also is falling into the same range. So I can use the same formula. Then it comes out to be 8 minus 13 by 2, which is 5 by 2, and the bond order is 2.5, which in turn means that bond order of C2 was 2, and when anion is formed, bond order increased. Because the bond order increased, what do we understand? If bond order increases, the stability increases. So when you convert C2 into its anionic form, the stability increases. The right answer is option A, but stay and verify rest of the options also using the same format. I hope you're clear about the shortcut formulae. Just for you to be more confident on this, I'll take one more example. Oxygen has got 16 electrons, and which formula should we be using? Total number of electrons is 16, which is falling in this range. So the formula should be 20 minus n by 2. And over here, n is equal to 16. So 20 minus 16 by 2, which is equal to 4 by 2, and its bond order is equal to 2. This is how you'll be using the shortcut formulae. But in case of any doubts regarding this, please let me know what your doubts are in the comment section below. For now, moving on to the next question. The isoelectronic set of ions among the following four options is. This is also a question from JEE Mains 2019, 10th April, shift 1. See how easy questions have been asked from this chemical bonding in 2019 mains. It's not the case only for 2019 mains, even in 20 mains, even in 18 mains. The questions from chemical bonding have been easy. If you focus a little bit, you'll be able to answer all the questions. So you have got four options. You need to choose the option which have got the isoelectronic set of ions. Isoelectronic species are those species which contain same number of electrons. So you just have to calculate the number of electrons in all the ions that you get to see amongst these options. In case of N3 minus, nitrogen originally has got what? It has got 7 electrons, and 3 minus, which means 3 electrons are added to nitrogen. So it is 7 plus 3, 10. Similarly, when you look at the total number of ions in O minus 2, it's 8 originally oxygen electrons and 2 extra added. So 10 is the total electrons. And similarly, F minus 10, Na plus 10, Li plus 2, Mg plus 2, 10. When you observe this, you just have to figure out the ions which contain same number of electrons and choose the suitable option. Technically, option D is consisting of those ions which contain same number of electrons. For example, N3 minus 10, O2 minus 10, F minus 10, Na plus also 10, right? And we have one other similar example question over here, which has been asked in 2017 mains paper. Back then mains used to happen offline also. So this is from the offline question paper. Anyways, even here you have to observe the four options and identify the set which contains isoelectronic species. Using the same logic, you have to identify the total number of electrons. O minus 2, originally 8 electrons, but then 2 electrons added extra. So 8 plus 2. Fluorine, originally 9 plus 1 added because of this charge, and Na plus 11 minus 1. If you have a cationic charge, you have to subtract. If you have anionic charge, you have to be adding the number of electrons. Cool. And doing the same when you calculate the total number of electrons in Mg plus 2, also in O minus, Na is atom, so you don't need to add anything over here. You can let the number of electrons be as it is. Mg plus, you removed 1 electron, and you have to identify the set which have got the same count of electrons. And technically option A has that, wherein you are having O minus 2 containing 10 electrons, F minus 10 electrons, Na plus 10 electrons, and Mg plus 2 10 electrons. If you observe very similar pattern of question in 2017 and also in 2019. From this you can see that the models of the questions can be repeated in mains. Not the exactly same question, but then the question models can be repeated, isn't understood. Even if you observe the options in both the cases, you're talking more or less about the same ions, right? You spoke about Mg+2 in both the places. You spoke about O- in both the places. You spoke about F- in both the places, and also Na+. So questions are very close by. This proves that you have to be solving the previous year question papers for sure. If you're someone who is preparing seriously for mains February 2021, make sure you at least solve past 15 years question papers, or at least follow this video series. Herein we are going to solve the previous year papers chapter wise. All right, so this is all for this video, guys. I'll see you in one other video. If you understood whatever we have discussed today, that's good, but in case of any doubts, ask me what your doubts are in the comment section below. I'll see you in one other video. Until then, bye everyone.